Okay, so today we're going to continue on with strengthening. I went back and I listened to the lecture from Wednesday, and I was not happy with the way I presented some things. So I'm going to re-record some of that content and post another lecture up. I think I expected too much sort of background knowledge and would have been able to kind of cherry pick out a couple points. But I think I need to hit that a little more in depth. So if anyone is confused from Wednesday, I'm sorry. So I'm going to re-record some stuff there and sort of adjust style. Also, the audio in the recorded lectures will be much better from now on because for some reason QuickTime was defaulting back to the internal microphone on the laptop rather than using the good external microphone when I started, and I figured out how to override that. So we should have better audio in the recorded lectures going forward from this point on. Okay, so we're gonna keep moving with solid solution strengthening and precipitation strengthening and hitting the main points. There's again a lot of equations in the reading and in the notes, and that's really more for the interested parties. What I really expect you guys to have readily available are the key sort of ideas, right? So what I hit in the lecture is the stuff I really want you to remember. There's a lot of extra material in the reading and in the notes. Okay, so solid solution strengthening, right? Making a alloy, a single phase alloy, is one of the two big tricks we have, and you can take it to the extreme with high entropy alloys now, which are equiatomic concentrations of multiple alloys, so that you don't have a single predominant species. So things like nickel, cobalt, chromium, tungsten, right? You put them all together in equal atomic proportions, and you get a single phase multi-component alloy. And the latest research and simulations are showing that it basically behaves just like a regular substitutional solid solution. There's nothing going on there that's actually different than what the basic theory that we're going to talk about for dilute solutions holds until it phase separates. If you phase separate, then of course the solid solution strengthening falls apart. But the main idea is, right, let's hear it one more time. Dislocations interact with things to give you strengthening. In this case, it's alloying elements, solute atoms, right? We're going to ignore the long-range stress field of the dislocation. Consider that a secondary effect that we don't need to worry about, okay? Okay, so let's think about a little model here. Here we have an edge dislocation. Here's our extra plane. Are the atoms above the slip plane under a state of compression or tension? Above the slip plane. Compression, right? What about below the slip plane? Tension. Okay, so this dislocation moves this way, and it encounters a small solute atom. When that dislocation encounters that atom, what does that do to this compression field? It relieves it, right? So is the dislocation going to be attracted to this atom or repelled? Attracted, right? So you've got a state of negative energy, right? What about if this solute atom was below the slip plane? Is it going to be attracted or repelled? Repelled, right? Okay. So on average, right, the slip planes are random and the solute placings are random. So on average, you're just as likely to experience a attraction and a repulsion, or a high energy and a low energy. So how does this give you strengthening if on average everything balances out? Any theories on that? It's impeding motion, so how does the right? It's obvious. Should be obvious how the positive energy, right? So you've got a repulsion, how that impedes motion. How about the attraction? Right? It wants to stay longer, right? Are dislocations perfectly straight, rigid bodies? No, they can bend. All right. So you have degrees of freedom in your system. Where is this dislocation going to want to stay? This particular one's going to want to stay on the solute, right? If we have another dislocation somewhere with a larger solute atom, this particular one will want to stay away from it, right? Or if this one were below the slip plane, it would want to stay away. Because this is under compression, right? So if you have a larger atom that's entering that compression field, it makes it, right? The atoms are already squished. Now think about,
Since it would be like making a compression right.
So think about an elevator jammed full of people, right? And a skinny guy gets out and I get in, right? Is everyone going to be more comfortable or less comfortable, right? It's the same situation there, right? And so the individual attractions and repulsions might be positive and negative, right? But on average, when you integrate over the energy, right, the fact that your dislocation wants to be near the negative interactions and wants to be away from the positive interactions, on average, you are impeding the dislocation motion because it wants to stay away from the high energy configurations and it wants to stay in the low energy configurations, right? You have to put in extra force to drive it through the high energy configurations, and you have to put in extra force to drag it away from the low energy, right? Where it will naturally fall into either one of those, states. Okay. Now, of course, there's some details that we need to consider here, right? So this is for edge dislocations, right? The stress field around a screw dislocation is pure shear. So this doesn't, if your dislocation is pure screw, it doesn't care what the size of the defect is, right? But how often do we encounter pure perfect screw dislocations? Never, right? Almost never, right? Because they're right? Dislocations are in a loop, right? And if the Berger's vector has to be the same for that entire loop, there's only 2 exact points on that dislocation loop that have no screw component, right? And then as soon as you break into partials, right, you don't have perfect screw component, right? So even though we say that the stress field for a screw dislocation is pure shear, your average arbitrary dislocation, right, will have a shear component, so it will have an effect, right? It won't be as strong as a pure edge, but it won't be 0. Right? From a mathematical point of view, we like to say this happens with probability 0, right? It's real, it's physical, but if you think about the entire amount of dislocation line you have in your material, it's the probability of it occurring is vanishingly small. Okay. Okay. So now let's imagine a different situation. That was for a substitutional atom. What happens when we stick something in interstitially? Right? When you do a substitutional solution, the stress field is essentially uniform. The strain field is essentially uniform around that body, right? You're taking something of smaller volume out and putting in something with larger volume, and it's going to push everything away uniformly, right? Well, what happens if we stick something in a interstitial location in BCC? Right? What is our biggest, right? Right? When does this come about? When will we see this? Carbon and steel, right? The most important interstitial. And so the cool thing about this is this does not have a symmetric distortion, right? This gives you an anisotropic stress field, right? Where if this is for a spherical, for a substitutional, the stress field around an interstitial, especially in BCC, or charged species, so in intermetallics or ordered compounds sometimes. But you get a strain field that's not spherical, these what we call these tetragonal distortions. And these are much higher in energy than a substitutional, right? And we'll look at that in sort of showing the magnitude. So you get much more strain thinning out of carbon and steel than you do in copper and aluminum at small quantities. The big one is nitrogen and niobium. You can get huge strengthening effects out of interstitials and BCCs. Okay, so this is just sort of the magnitude, and again, we're not going to go through the derivation, but what goes into here, right? So the shear modulus, the Berger's vector, the size of the atom. This E sub B is essentially an effective strain that tells you the size of the distortion. So you can think about that as like the volume mismatch, right? It's a unitless parameter that tells you how big the distortion is and how far your dislocation is from the solute atom, right? And that tells you your those are the main physical things that go into the energy, right? And remember, this is always taken as a negative energy, right? This is always an attraction, right? For perfect screws, it's 0, so we're always going to be somewhere in between this sort of range. Again, the mathematics is not very important for this. Just the key terms that go into it. Okay, so that's one effect from solid solution strengthening. We can also get an effect from having a modulus mismatch. Right? Why would if I had atoms that were exactly the same size, but I had two materials that were different shear moduli, how would that give me an effect? Wait. I suppose I shouldn't have the answer up on the slides. But I'm not getting an answer even when people are reading it. Right? What's the energy of a dislocation? Right? GB squared, right? So shear modulus, right there. Right? What happens if I put in something that increases the shear modulus? Right? I put in a stiffer atom. It's going to increase the energy of that dislocation line when it passes by it. If I put in something that is not as stiff, more compliant, it's going to lower the energy as that dislocation line comes up to it. Right? Okay? So size effect was always a negative attraction, right? But because of the argument, the statistical argument that you always encounter them with equal frequency. However, a stiff dislocation is going to give you a greater energy whether you come at it from above or below, right? So that's always going to be positive, right? And a more compliant atom is always going to be negative, right? So there is no statistical averaging that happens here. There is a quick warning, right? So in the reading, I think the language is a little confusing that the author uses, Courtney uses. He uses hard atom for stiffer and soft for more compliant, which is the same language he uses for hard obstacles and soft or weak obstacles. So it's confusing because a hard atom is a weak obstacle and a soft atom is a hard obstacle, and right? So just when you're going through this, keep this in mind that it might be a little confusing. Okay, so again, we're going to go through it without derivation, but what goes into this? Well, obviously the modulus of our material, right? This is again a dimensionless parameter that characterizes the modulus difference between our two atoms, right? So there's this. You'll notice going through this, they all sort of have the same sort of things in them. They all have this dimensionless strain-like parameter that quantifies a distortion-like term, right? The distance squared, right? The radius of the atom cubed, Berger's vector, right? And the only difference between screw and edge is that, remember, the stress field of an edge dislocation has this Poisson's ratio term in there, right? So the 1 minus Poisson's ratio, so we're dividing by a smaller number, so the energy for a pure edge is roughly 3/2 that for a perfect screw, right? Because Poisson's ratio is always about 0.3. Okay, so we have to combine these together, right? So here's our attraction, right? Our size effect is always negative, right? Our modulus effect can either be negative or positive depending on the stiffness of our substitutional atom. So when we have a small, more compliant atom substitution, we get, or not necessarily small, when we have a more compliant substitutional atom with a greater size difference, right, is where we get our optimum hardening, right? But you got to remember our Hume-Rothery, right? So what's about the maximum amount that we can put in to get strength, a solution across the whole range? It's about 15%, right? So if we're significantly have more of a deviation than that, we're only going to be able to put our solute atoms in small concentrations before we phase separate. Right? Now, if we put in a stiffer atom, we now have a positive modulus effect and a negative size effect. So we get overall less strengthening when we add those two energies together. Right? And so the overall strengthening is quite different between spherical or substitutional and tetragonal interstitial, primarily interstitial and DCC. it's roughly a difference of about 20, right? So the effect is G by 100, G by 5. Right, sort of the maximum that you're going to be able to get out. Okay, so let's take a look here. Here is substitutions. So this is square root of concentration here, square root of concentration here, and so aluminum and copper pretty weak, right? So if we do some brasses, we can get a lot better. But take a look at the effect of steel and iron, right? This is the change in the stress and the yield stress, right? So 140 MPa with a relatively small amount of carbon addition, right? If you keep extending that out, you look at the effect of nitrogen and niobium, it's huge. You'll never be able to get those kind of strengthening effects from a purely substitutional alloying. Right? So, coming back to the main ideas of the course, right? We want to talk about, as we're going through the different alloy systems, alloy design. Right? And so understanding what the alloying elements are going to do, right? Both in the region where it's phase separated, but because even when you have an alloy that separates, right? We'll take this as becomes really important in superalloys. You still have significant solute strengthening even in the phase separated region, right? I mean, it's very rare that you go to pure line compounds, right? We're usually quenching stuff in, right? So understanding where your solute atoms are going and what the effect they're going to have on the properties is key. So this will keep coming sort of up again and again. Then the other major strengthening mechanism is particle or precipitate strengthening, right? And so in here, instead of individual atoms interacting with dislocations, now we've got dislocations interacting with a small second phase particle, right? And you can make a very hand-waving argument, right? And say that this should be a stronger effect because now I've got a bunch of solute atoms all stuck in one spot, right? So it should be a bigger magnitude than a single solute atom, right? So from a very simple cursory idea, we should have the notion that this is a stronger effect than you would get from pure substitutional solute strengthening. Okay. So basically, the general ideas are, if I've got dislocation that interacts with a particle, right? The degree of interaction is going to depend on a lot of things, right? The particle size, right? How big the particle is, the number of particles that I have, the separation between the particles, the shape of the particle, right? Needle-like particles are going to interact differently than small spherical particles, right? And the nature of the boundary between the particle and the matrix, right? If I have a fully coherent interface with my particle, it's going to be easier for dislocations to go through than if I have a incoherent, right? And so we have to think about these things. So of course, non-spherical particles can sometimes have a bigger effect. For just the purpose of general principles, we're only going to be talking about spherical particles. But remember that shape does can have a play. So the first thing is coherency, right? So if I have an interface that looks like this, rather than an interface that looks like this, it's not too much of a stretch to say it's easier for a dislocation to come through here, right? I've got nice correspondence between my atoms. This acts like a grain boundary. We talked about how grain boundaries can act very much as sources or sinks for dislocations. A dislocation comes through here, and it finds itself gobbled up by the interface, right? And when it does go through, it has to change planes and leave a debris. There's debris that builds up in the interface, so it becomes a messy situation. So if a dislocation comes up on a particle, it's much more likely to cut it if the particle is coherent and small, right? It's much more likely to go around it when the interface is disordered, right? So all of these arguments here, these are sort of, they're not very rigorous models. These terms are very difficult to treat rigorously, right? But you've got a couple different things that happen. First is the interface coherent or not, right? But you typically have a volume mismatch, right? It's rare to have a second phase particle that has the same specific volume as the alloy, right? So we have all sorts of coherency strains around this particle. So our lattice is distorted by an elastic field that's going to interact with those dislocations much in the same way that a substitutional solid individual atom, right, that's either smaller or larger than the matrix is going to interact. And that's difficult to calculate except in very specific circumstances. But we can make some estimates, right? And again, what goes in here, this is our distortion term to the 3 halves, so slightly larger. Right, we've got this factor of 7 out front. We don't have anything divided by pi on the bottom, right? But it has the same general sorts of terms: the shear modulus, the radius, the volume fraction, the Berger's vector, right? All that's under the square root. So the same physical terms keep coming up over and over again. It's just they're arranged in slightly different ways, right? Which makes sense because we're talking about how hard it is for a dislocation to move through something, right? So you expect the same ideas to keep showing up over and over again when you're talking about how defects move. Okay. We also have the modulus effect that we need to consider about, right? When a dislocation cuts into a particle that has a different shear modulus, different stiffness than the matrix, we're going to alter the line tension of that dislocation, right? So the line tension of the dislocation is GB squared. Out here we're G of the matrix, in here we're G of the particle, right? If this is stiffer, the line energy in the dislocation has a higher line energy. If we're inside, it has a lower energy, right? So if we're cutting this particle, right, if it is a stiffer particle, we have to apply a lot of force to get it through, right? And the amount of force we're going to need is going to keep increasing proportional to the change in energy and the cross-sectional area of the particle, right, as we cut through, right? And then in the other sense, right, if we get over the other effects, it's going to want to come in because it will reduce its energy, but then we have to work to get it out. Because once we're at the halfway point, now as we pull, we're increasing the energy of that dislocation. All right? Yeah.
So from your slide, I think when our 32, there's a line you're saying that Modulus Effect is can act as solid solution strengthening. So would you say this as like a kind of precipitation hardening, or
So this is completely precipitation hardening. Right. So there's a modulus effect in solid solution strengthening, and there's a modulus effect in precipitation hardening. And they're both the same thing. The fact is that the stiffness, elastic properties of the local environment are going to affect the energy of the dislocation. Right? It's whether it's just the elastic field around an individual atom, right? The interaction of the elastic field of the dislocation with the atom, or whether it's an interaction of the elastic field of the dislocation with an entire particle of the same material. But it's the same effect, right? Right. Okay. Then we have what always confused me why it's called chemical strengthening. But really, when we shear this particle, a dislocation comes through, we make steps, right? So we're increasing the surface area of the particle, right? Surfaces all have energy, right? And so if we take a spherical particle and we make it elliptical with lots of steps on it, we can potentially significantly increase the surface energy of that particle, right? So each step we make. All right. So this is generally a pretty weak effect, right? We're not, an individual cutting event adds only a very small amount of surface energy, right? However, if the particles are very small, right, in the earliest stage of precipitation, then a step can be significant, right? So if you think about, right, what does surface area, what's the formula for surface area as a function of radius? Right? So what happens if our radius is, right, if we calculate the volume of our particle, the ratio of the surface area to the volume of the particle, right? As r gets small, right, it blows up astronomically, right? So the amount of grain boundary area in a nanocrystal, right, basically, if you think about the probability that an average atom is going to be near a grain boundary, even though we have a ton of grain boundaries in metals, in a large grained material, right, something that's, say, 20 microns, right, not necessarily large, but the probability of an individual atom being at a grain boundary is very small. Now you shrink that grain volume down to nano size, nanograined, ultrafine grained material, the probability that an average atom is going to be at an interface is astronomically high, right? So if you think about atoms that are on the order of angstroms, grain sizes that are a couple nanometers, right? That means you only have 20, 30 atoms, right, across. So your whole thing is basically grain boundaries. The same thing here. If I make very small particles, right, if I have particles that are tens or hundreds of atoms, it's almost all surface. So cutting through that adds a shear offset, and that can add a significant amount. Once the particles are approach micron size, this effect almost essentially washes out because you're adding such a small amount of surface area. Okay? And then an important one that we have to think about is order strengthening. Right? So here's sort of a schematic. Right? We've got our stacking sequence. In this case, this is A, B, A. Right? So two-dimensional cubic or 3D HCP. Right? But in this case, right, our 2D cubic, right, if we pass a edge dislocation through and we offset everything by 1, now we have a stacking fault, AAB, right, instead of ABAB, right? So this is going to depend on the antiphase boundary energy of our particle. Real faults are much more complicated than this, right? You ever want to get into a dizzying conversation about stacking, talk to Professor Mills, right? We'll talk about complex stacking faults, intrinsic stacking faults, superlattice extrinsic stacking faults, right? Hundreds of different nomenclatures of how you can disrupt the order, right, and what the different energies are and how things move from one to the other. But the main idea is whenever we pass a dislocation through, right, we're going to alter the stacking of our precipitate, right? And if this is an ordered structure, right, like gamma prime particles in nickel superalloy, right, this can have a very high energy penalty associated with it, right? Right. So basically, the thing is, it's always just going to be proportional to the amount of surface area that is affected and the antiphase boundary energy of your particle. Okay. So non-deforming particles. All right. So let's. If I've got a particle that can't be cut, right? What's going to happen? A dislocation comes up to these particles. It can't cut through them, right? They're too big. The interface energy is too much, right? So what's going to happen? Well, there's space here. The dislocation can still move forward between them. It's going to bow around. One thing I don't like about Courtney is what's missing from this picture. Right? Whenever we make drawings of dislocations, what do we need to include? Right? A sense. I don't know if this is a positive or a negative dislocation, right? So I should have arrows here giving me a sense. Right? And so if we follow the arrows around, this is going to start to bow out. I have my arrows going this way. Right? So now I've got an arrow here going here. Got an arrow here pointing out. So these two are now of an opposite sense, right? Relative to each other, this is positive, this is negative, right? I'll make a drawing on the board in just a second, because I'm seeing some confused looks, so I'll draw the arrows on. But then these two, once we bow out far enough, are attracted to each other and will annihilate because they're of exactly opposite sense. And that will allow this dislocation to pass through, and it will leave behind two loops around the particles. All right? Okay, so we didn't have a camera set up to record what I put on the board during today's lecture, so I'm just quickly re-recording that bit offline. So we were talking about the stress required to bow a dislocation around some particles here. And so what we did is we set this up so the distance between the particles was L. And if the particles had a diameter of 2 times the radius, that had a radius of r, the distance, the width of this actual channel that the dislocation has to go through is going to be L minus 2r. Right? So that's just the geometry of R. The geometry of this system. And so now let's pretend we have a dislocation here. Right? Arrows to give the sense. And as the dislocation moves up, it's going to hit these particles and eventually it's going to start to go up, bow between them, and this angle here, we'll call that phi. Right? Remember, we always need to keep our sense of our dislocation line. Right? And so what we're interested in is how much bowing do we get for a certain amount of force, right? So if we remember the line tension of a dislocation is going to be GB squared by 2, right? And so if we do our vector and we want the force that's resolved in a direction in the vertical direction, right? That's going to be 2 cosine phi GB squared by 2. And then we need the actual force exerted on the dislocation by the shear stress, right? So this is the line tension, right? Right, which acts to pull on the dislocation like this, and at any given point, right? At this point, we're asking what's the line tension that's acting to pull right in the normal component here, right? So at this point, there's a tension, right? This angle here is theta. We want to know what the part of this force that's acting perpendicular this way, right? And so that's this 2 cosine theta GB squared by 2. Right, of course, these twos cancel. So now what we want to know is what is the force acting on this dislocation line, and from the Pech-Kohler force, for Pech-Kohler equation, we know that's tau b, right? And if we, right, and that's per unit length. Right? And now we want to convert this to force on this dislocation line per obstacle, right? And so only the length perpendicular to the shear stress is going to matter, right? So we can call that L minus 2R tau B, right? And since, does that actually show up? Okay, good, I can still see that. Right, because this is a force balance, right? These two need to be equal so we can set it and then do the algebra. Right? And we get tau equals GB. Oh, I still got my cosine in here. I haven't gotten to that yet. Right? This is not right. Yeah, GB squared B GB cos phi by L minus 2R. Now, so that's for any arbitrary angle, but if we think about what's happening with dislocations, right, eventually this angle phi, as this gets more and more bowed out, gets closer and closer to 0. So the critical tau when this happens, cosine of 0 is 1. Right? Just becomes GB over L by 2R. And at this point, notice the sense is the same across the whole dislocation line, but locally here, we've got an arrow pointing down and an arrow pointing up. So these two regions are now attracted to each other. So they'll meet and annihilate. And then what we end up with is particles with a dislocation loop around them, and a dislocation that has bypassed the particles by bowing around them. Right? And that's Orawan bowing, and that's the exact same force balance that you guys did, I'm sure, in your defects in structures class when you looked at the force required to operate a Frank-Reed source. So here we've got a dislocation between these two pinning points, and the dislocation line is basically, you can imagine it going into the board, right? And this is going to continue to bow out, right, until eventually the same thing happens, right? And so for Orawan looping, it's the same balance of forces that you did here, right? So hopefully that's a quick refresher and not the first time you've seen that analysis. Okay, thanks. So shearing is the exact same analysis, except once you don't go all the way to the full 0 degree angle, right? You start to bow through the particles, then when your force gets high enough to overcome all of those effects, right? Your coherency, your modulus, your chemical, your anti-phase boundary. Once you have enough energy to go through that, then you pop through. So these are particles that won't shear, right? So we've got, right, and that's this slide. There we go. Okay. full screen. And then, right? So there's a balance, right? That we have to consider, right? That, man, I wish this resolution of this projector was better.
It's like that on the printed slides too.
Is it?
Well, we print out the
It's
slides.
very small. Okay.
On
So,
some of the other bigger ones, they're still
okay. Right. So basically, you've got a balance between cutting and bowing. Right. When your particle is small, it's much easier to cut than it is to bow around them. When your particle is large, it's easier to bow around them than cutting. Right? So if this is the force needed to do both, right, you want to find the particle size that maximizes right where they intersect. Right? I've got one function that's constantly monotonically increasing, one that's monotonically decreasing. Their intersection has to be the maximum. Right? So that's the radius that you're trying to get your particles to. Right? Because it's going to operate on whichever one is easiest, right? If it's easier to shear, it's going to shear. If it's easier to bow, it's always going to bow, right? Nature will find the minimum energy, right? So you want to make that minimum energy as difficult as possible to attain, right? And this will be very important when we talk about aging in aluminum alloys in starting next week, right? Because if we overage, we grow our particles too big, and we weaken our, right? If we underage, our particles are too small and they're too easy to cut. Right? So you want to get it just the right amount, so you've had time for your particles to grow, but not grow too big, so that you weaken your alloy.